Hello everyone, welcome to lecture 37 of the online course on Introduction to Microwave and Optical Metamaterials. Today's lecture will be on negative index metamaterials. Here is the lecture outline. We will first look into a couple of reversed phenomena in negative index media. We will discuss about determining the sign of the refractive index, left-handed nature and anti-parallel vectors. We will discuss modified Snell's law and take up examples of other reversed phenomena. And then we will look into negative refraction in microwave frequencies. What are the challenges posed by the naturally occurring negative index material and how you can overcome the natural limitations with metamaterials. And at the last we will see some early experimental demonstrations at microwave frequencies. So, first of all, what would be the sign of the refractive index? Okay, if you have a media where both permittivity epsilon and permeability mu are negative. So, the choice of the sign can be resolved by the causality condition. So, how refractive index is defined? Refractive index n is defined as plus minus square root of epsilon mu. Now, when epsilon equals -1 and mu equals -1, it is not immediately clear that whether n should be +1 or -1, and that is where the ambiguity lies. Now, there you can bring the causality condition. It says that for any realistic passive material, there must be some energy absorption, however small it is. Okay? That means for both epsilon and mu, there should be a small positive imaginary part. In that case, we should write epsilon as -1 plus I delta 1. Delta 1 is very small, but it is positive. Similarly, mu should also be written as -1 plus I delta 2, where delta 2 is also small but positive. Now, mathematically, when you resolve it, you can see that the refractive index will now take this particular form, where you have n, which is given as plus minus square root of -1 plus I delta 1 times -1 plus I delta 2. So, that can be expanded and you can separate the real and the imaginary part and can write as plus minus square root of 1 minus delta 1 delta 2 minus I delta 1 plus delta 2. Now, this can be approximated as n equals plus minus 1 minus I delta 1 plus delta 2 by 2. Now, what is the conclusion here? You can see that causality will require that the imaginary part of the n must be positive, and that will represent wave attenuation in that medium. So, in order to satisfy that, you have to choose this outside minus sign, so that you get n equals -1 plus I is small positive imaginary part, and that is how you actually get this -1 sign when both epsilon and mu are negative, right. So, that is the final thing, that when the real parts of epsilon and mu are negative, the real part of n must also be negative. Now, let us look into the left-handed nature and the anti-parallel vectors. So, in negative index materials or NIMs, the relationship between the electric field E, magnetic field H and the wave vector K is fundamentally different from the conventional materials. Okay. First, you can talk in terms of phase advancement. You will see that in a negative index medium, you will have the phase velocity of a wave that is directed against the flow of the energy. Okay. That means K and S will be basically in the opposite direction. So, for a wave which is described by e to the power I n k z minus omega t, if you have negative n, that is basically telling you that the phase becomes advanced in the direction of propagation rather than getting retarded. So, that is the feature of phase advancement in negative index materials. Next is the vector relationship. Now, Maxwell's equations define the orientations of the fields like this. So, you have seen this earlier as well. K cross H will be minus omega epsilon naught epsilon E, and k cross E will be equal to omega mu naught mu into H. Okay. Now, that is where the comparison between the right hand and the left handed media will come. We have discussed this earlier in the previous lecture. So, in the common material where you have both permittivity and permeability positive, you will see that the vectors E, H and K form a right handed system where the axes are mutually orthogonal, right. In the case of a negative index material where both epsilon and mu are negative, these vectors form a left handed system, and that is why negative index materials are also called as left handed materials. Another important aspect is the energy flow. The most crucial consequence is that the wave vector k is going to be anti-parallel to the Poynting vector S, which is calculated as E cross H conjugate. Okay? That basically represents the direction of energy propagation. So, your wave vector is going to be opposite to that. So, that also gives you some interesting effects like modified Snell's law. So, this is one of the most intuitive result of negative refractive index, that how it is going to change the law of refraction. So, in the normal situation when you have both materials or conventional materials, that is permittivity and permeability are positive, okay, you have this sort of refraction. Okay. So, you have the incident angle theta I, theta t, okay, on the opposite side of the normal, right. But in the case of negative refraction angle, you will see that if N2 is negative, in that case you will see that theta t is basically minus theta t. Okay. That means to satisfy this equation, because this is negative, the angle also has to be negative. That means the angle, the reflected light, instead of going in this direction or like this, it will basically be on the same side of the normal. Okay. So, this happens when your light is going to pass from a positive index medium, that is say N1 greater than 0, to a negative index medium where you have N2 which is negative. So, in that case the angle of refraction theta t must be also negative. So, that is making the beam or the refracted beam to bend on the same side of the normal as of the incident beam. Okay. So, what is the physical justification of this kind of behavior? So, this behavior is basically required by the law of momentum conservation, which basically dictates that the tangential component of the wave vector must be continuous across the interface. So, if you do that here between the interface of a normal and a negative index material, you will see that the k has to be in this particular direction to satisfy this condition. Now, since your energy ray or the Poynting vector in the negative index material, okay, is basically pointing opposite to the wave vector, so the energy flow is happening this way. So, your k vector has to be in the opposite direction. So, this is completely unusual and it is not seen in any regular material. So, this is the way energy is flowing. So, in this material, in the regular material you see the energy flow and the k is in the same direction, but inside the negative index material the energy flow is downward, but the k is upward. Now, let us look into examples of other reversed phenomena. So, this kind of unique phase reversal that you see in negative index materials can also lead to the reversal of several other fundamental optical effects. The first one is Doppler effect. So, let us first see what normally Doppler effect is. Doppler effect is basically the change in a wave's frequency as perceived by the detector due to the relative motion between the wave source and the detector. So, here you can see this is a Doppler effect in the right handed substance. So, A represents the source of the radiation, B is your receiver. So, this is the flow of energy and this is also the wave vector, okay, and say the source is basically moving with a velocity v towards the detector. In that case, the perceived frequency omega will be described by this equation where omega equals omega naught plus k dot v. So, omega naught is basically the true frequency of the source, k is the wave vector that is along this direction, and v is basically the source velocity with respect to the detector. Now, in normal Doppler effect, what happens? In conventional materials where you have both epsilon and mu as positive, your wave vector k points from the source to the detector, and as the source approaches, okay, that means you are basically seeing that the k and the v are basically in the same direction. So, that will make the dot product of k dot v as positive, and that will increase the perceived frequency. On the other case, when you have the source moving away from the detector, that means the v is in the opposite direction, that particular dot product k dot v will become negative, and that is why you will see the perceived frequency to be lower than the original or true frequency. Now, what happens when you see in the case of a left-handed medium? So, in the left-handed medium, A is again source, B is the detector. So, the energy flow is happening from source to detector. So, this is the direction of S, that is the energy flow, but the wave is flowing in the other direction. So, K is in the backward direction. So, that gives rise to reverse Doppler effect in negative index media. Because in this kind of negative index material, the K vector is unique and it basically points from the detector to the source. So, when the source is basically approaching the detector, that means you will have V going in this direction, which is opposite to the direction of K, that means they are anti-parallel. So, in that case you will get a negative dot product, and that will make your perceived frequency lower than that as compared to the normal Doppler effect. So, here it basically works other way. When the source is coming towards the detector, okay, you will see that the frequency is basically reducing. Another interesting phenomena could be the reversed Cherenkov radiation. So, to understand this, we need to first understand what is Cherenkov radiation, right. So, this is a radiation emitted when a charged particle travels faster than the phase velocity of light in a particular medium. So, here let us consider a situation when you have electron speed, that is beta c, which is less than the speed of light. Okay. So, when you consider the velocity slower than light, what happens? That is the case, we will see that this is the electron, these are two positions A and B, okay, and this beta is basically less than 1 by n. So, you have the electrons slower than light. Okay. So, when that is the case, okay, you will have the electromagnetic wave basically generating from this electron expands away from it in concentric spheres, just like this. Okay. So, in this case what is happening, the particle never catches up to the waves it creates, and that is why no shock wave is basically formed. So, once again, this is the situation when the electron speed beta c is less than the speed of light in the medium, that is c by n. Okay. So, the electromagnetic waves it generates basically expands away from it in this kind of concentric spheres. Now, what is the other case when the particle travels at a speed faster than light? So, here we are considering the electron to travel faster than light in that medium. So, what is happening? It can continuously outpace the spherical waveform it is generating. Okay. So, in that case, these individual wavefronts can overlap and interfere constructively, forming a large or you can say forming a single coherent waveform which is in the form of a cone. Okay. So, this cone of light that you see is basically the Cherenkov radiation. So, on the right hand side you can also see that you can determine the cone angle. So, the angle of this cone is basically determined by the ratio of the two speeds. Okay. So, in the time it takes the light to travel a distance of c by n, the electron basically travels a distance of beta c. Okay. So, that is how this particular distance is. This is the electron distance, this is the distance of light in that medium. So, you can basically see that the geometry of this overlapping waves basically form a right angled triangle. So, like this. Okay. So, you can actually get, and this particular angle is called theta c. Okay. And you can see that the relationship will be nothing but cos theta c will be equal to 1 by beta n. This c and this c will cancel out. Okay. So, that is how you can obtain this particular cone. Okay. Now, what you see in a negative index material, because your n is negative, your cos phi will also be negative. That means, you will have reversed a Cherenkov radiation, right. So, the angle here you have to understand that because cos phi is becoming negative, that means the angle phi must be obtuse, that means greater than 90 degree, and in that case what will happen, the Cherenkov radiation is basically emitted backward relative to the particles direction of motion. So, this is completely unusual and opposite of what happens in a conventional material. So, now let us discuss the challenges that you see with naturally occurring negative index materials. The first problem is that no known material, natural material has a readily observed negative index of refraction. So, you do not find such material in nature where for a particular frequency it is giving you simultaneously negative permittivity and negative permeability. So, what are the conditions of negative index that we all know? That a material should have a negative refractive index if both its electric permittivity epsilon and magnetic permeability mu are simultaneously negative at the same frequency. Now, this is a problem because in nature you will see there is frequency mismatch. By that I mean that some materials exhibit negative permittivity like noble metal at high optical frequencies like terahertz and above. However, they do not have permeability negative at that range. Similarly, there are materials with negative permeability, something like antiferromagnets, they have this kind of negative mu, but their natural magnetic resonance will fade away at high frequencies where typically the negative permittivity occurs or takes place. So, it is very difficult to have the frequency matching where you will have both negative permittivity and permeability at the same time in a particular material. So, what is the solution? The solution here is to overcome this kind of natural limitation with metamaterials. So, the critical step here is to create a negative index material, okay, by overcoming this low frequency limit of the magnetic response that you find in conventional materials. So, you have to basically see magnetism at high frequency, okay, then only you will be able to get this negative permeability at high frequencies. So, that is where metamaterial solutions are important. So, researchers basically used artificially engineered structures, or their unit cells are called meta atoms. Meta means artificial, we have already discussed this earlier. So, they can create strong magnetic coupling to electromagnetic fields at high frequencies. Okay. So, this approach has basically enabled creation of negative index materials across a wide portion of the electromagnetic spectrum, and when I say wide portion, it basically ranges from microwave frequencies up to visible light. Now, we will now look into some early experimental demonstrations of negative index materials at microwave frequencies. So, the first experimental demonstration of this kind of negative refraction that was obtained before 2005 were mainly focused at microwave frequencies, right. So, what are the key building blocks here? So, this early negative index materials were basically constructed by combining two main components. First, you need to have a periodic array of thin wires that can produce negative effective permittivity. So, you are getting epsilon negative, and then you need a periodic array of split ring resonators, okay, that can create negative effective permeability. So, you are getting mu also negative. So, here you are seeing the photograph of the first left-handed metamaterial sample that was built by the University of California, San Diego. Okay. So, this sample, as you can see, consists of square copper split ring resonators, okay, and also there is a copper wire strip, both overlapped, okay, on a fiberglass circuit board material. So, the rings and the, as you can see here clearly, the rings and the wires are on the opposite side of the boards. So, you are basically having a array of wires which were giving you negative permittivity, and then you also have a array of split ring resonators that were giving you effective negative permeability. And these two things were, the boards were cut and assembled into a interlocking lattice, and that was giving negative permittivity. So, this is a famous work, and this was the first demonstration by, as I mentioned, by this UCSD group, okay, and this structure successfully verified a negative index of refraction by demonstrating refraction according to the modified Snell's law. And you can see here in figure 4b. So, here they are plotting the transmitted power, okay, at 10.5 gigahertz as a function of refraction angle for both a Teflon sample, which is the dotted one, and also a left hand material sample, which is the solid curve. Now, these two curves are basically normalized such that the magnitude of both the peaks are matched at 1. So, here you can observe for Teflon sample, the refracted power peak was measured to be 27 degree, okay, somewhere here, corresponding to the positive index of refraction, which is 1.4 plus minus 0.1. But on the other hand, if you look into the left hand material sample, the peak was recorded at minus 61, okay, from which you can deduce the index of refraction to be minus 2.7 plus minus 0.1. So, this is telling you that negative index material is going to give you negative refraction. So, the beam width was set by the diffraction at the exit of the incident channel, and the angular sensitivity of the detector, okay, and is similar to the bandwidth that is measured without a sample in place. So, that is how the experiment was performed. So, this was the first one, and later on a 3-dimensional negative index material cube, which was made using similar design, also confirmed this kind of findings, removing any doubt regarding the feasibility of fabricating negative index materials. So, this wire and split ring resonator combination became a standard prototype for most early research in this particular field. Now, they also did the calculation of the refractive index. So, the index of refraction for this left hand material sample was also measured, and they confirmed it to be negative within a specific frequency band, as you can see in this particular figure. Okay. So, here you can see the blue curve, which basically corresponds to the data of the Teflon sample, okay, and then you have a black curve. So, that is basically for the left hand material data, and there in the black curve you see some dotted portion, that is basically indicating that here the index is expected to be either outside the limit of detection, which is basically plus minus 3 in this case, and should be within 3 plus minus 3, or it is dominated by the imaginary component, and therefore it cannot be reliably determined experimentally. So, they are given as dotted lines. Along with that, the red ones basically show the theoretical calculated value of the left hand materials. They are also in the red, you see the dotted lines, they basically tell you the imaginary component of the theoretical expression of the refractive index. Now, what does this comparison with Teflon tells us? That if you have a Teflon sample, it basically shows a constant flat refractive index across the entire measured frequency band. So, it is basically X band here. Okay. In the case of left hand material, the first thing that you notice is the dispersive nature, that is it is frequency dependent. Okay. So, this negative index behavior is highly dispersive. So, it changes significantly with frequency, and this particular finding is consistent with the theoretical prediction as well. And why theoretical prediction was needed? Because this basically shows that the frequency dependent models that we discussed earlier in the lectures, okay, they also can predict the material permittivity and permeability to a good extent. So, all these things confirms that using metamaterial you can realize negative index materials which are not found in the nature. So, with that we conclude this lecture. If you have got any query regarding this lecture, you can drop an email to this email address mentioning the course name and the lecture number on the subject line. Thank you.